Hello there and welcome to the June 2019 paper. Here we're looking at question 5. So the complex numbers z1 equals minus 2, z2 equals minus 1 plus 2i, and z3 equals 1 plus I are plotted in figure 1 on an Argand diagram for the complex plane where z equals x plus yi. Explain why z1, z2 and z3 cannot all be roots of a quartic polynomial equation with real coefficients. So the reason is because if z2 equals minus 1 plus 2i is a root of a polynomial with real coefficients, then minus 1 and minus 2i would also be a root. For the same reason, if 1 plus I is a root, 1 minus I would also be a root. Because complex roots come in complex conjugate pairs. So therefore we have now 1, 2, 3, 4, and the root minus 2, which doesn't have a complex conjugate because it's already a real value. So therefore we would have 5 roots. Therefore we would have 5 roots which would not fit in a quartic. Would not fit in a quartic. And there we are, that's the answer for part A then. So a little explanation that roots inside polynomials with real coefficients come in complex conjugate pairs. Moving on to part B now, show that the argument of z2 minus z1 divided by z3 minus z1 equals pi by 4. Okay, let's get to proving that then. So what z2 minus z1 means is that it will be at it will be the vector from z1 to z2. So it'll be that vector there. And z3 to z1 will be this vector here, going from this one to this one. So what we basically need to show is that this angle here is a pi by 4 angle. Okay, then let's just do the maths on it then. So we're going to be doing the argument of z2, which is minus 1 plus 2i, minus z1, that would be minus 2, so plus 2, over z3, which is 1 plus I, plus 2 again. So that's going to equal the argument of 1 plus 2i over 3 plus I. Let's times top and bottom by the complex conjugate. So it's going to be 1 plus 2i times 3 minus I over, on the denominator it's going to be 3 plus I times 3 minus I, which is equal to the argument of 3 minus I plus 6i minus 2i squared, that would be plus 2 over, that's going to be over 9 minus 3i and plus 3i and then plus the 1. So therefore this is going to equal to the argument of 5 plus 5i over 10 let's just simplify that. So that's going to equal the argument of a half plus a half I. So now we can now work out what the argument of this is going to be equal tan inverse of the imaginary part over the real part, which is going to be equal pi by 4. So there we are, equal to part B. Hence show that arctan of 2 minus arctan of a third also equals pi by 4. So what we'll now do is we'll do these arguments separately. So let's go back to this point here, that arg of 1 plus 2i over 3 plus I equals the argument of 1 plus 2i minus the argument of 3 plus I. So again, these are both in the top right quadrant, so these arguments would be quite easy to work out. So it's going to be tan inverse of the imaginary part over the real part, so 2 over 1, minus tan inverse, again imaginary over real, 1 over 3. So therefore this is equal to, now arctan is the same as tan minus 1, so I'll write it in proper form here. Arctan of 2 minus arctan of a third will equal this thing here, and through the lots of equal signs will also equal pi by 4. So there we are, that's the answer for part C. Let's now move on to the final part, part D. The complex numbers z1 equals, all plotted on the diagram, show on the diagram the set of points on the complex plane that satisfy the inequality z plus 2 is less than or equal to z minus 1 minus I modulus. Now these modulus things here representing distance. So what the left hand and the right hand side is saying is that we want the distance from minus 2, that would be the solution effectively to this modulus here. The distance from minus 2 is less than or equal the distance from 1 plus I. So we have this point is z1, that is the point minus 2. This point here is the point 1 plus I. And now we want the line to be a perpendicular bisector of the minus 2 and 1 plus I point. So this line is going to be a perpendicular bisector of minus 2 and 1 plus I. So given that this line here has a gradient of a third, it's going to be 1 up, 3 across. This line that's going to come into place here is going to have a gradient of minus 3. I just want to check which side z2 is on. So if I plug z2 into both sides of my inequality, I'll see which side z2 falls on, because it could fall on this side, could be on the line though. So let's just try it out. So plugging in z2, which is minus 1 plus 2i, minus 1 plus 2i, and then plus 2, and then the other one will be minus 1 plus 2i, and then minus 1 minus I. Let's just work out both of these moduluses. It's going to be 3, it's going to be 1 plus 2i, so that's going to be root 5. And then on this side here, that's going to be minus 2 plus I, so 2 squared plus 1 squared is root 5 as well, so they are equal. So z2 is going to be bang on the line. What about 0, 0? If you plug in 0 into z here and 0 into z here, then you're going to get a modulus of 2 here, which will be 2. And if you plug in 0 here, you're going to get a modulus of 1 squared plus 1 squared, square rooted, that would be root 2. So actually, root 2 is going to be higher. So what does that mean? So the distance to here is 2, the distance to here is root 2. So if it's a perpendicular bisector, it needs to be equal. So it needs to actually be going through a point somewhere like there. So it's going to have a gradient of -3, because the distance of any point on this line should be equidistant between these 2 points here. So therefore that distance there and that distance there, it doesn't look equal on my diagram, but they should be equal in theory. So it should be going down past the y-axis on the negative side. So here we are, that's the line of the perpendicular bisector, but now we want the shaded region. So the shaded region, now let's have a look at this statement here. The distance from -2 is going to be less than or equal to the distance from 1 plus I, so that's this side here. On this side here, all the coordinates to the distance to -2 is going to be less than the distance to 1 plus I. Take this coordinate here, for example. The distance to -2 is far less than the distance to 1 plus I, so therefore it's all these coordinates on the left-hand side there. So there we are, that's the answer for this question here, then it's the answer for question 5. Let's move on to question 6.